One request, 12 moves with sidecars, 7 with eBPF. Why? The packet leaves the direct path, climbs into a proxy, then drops back into Linux. That detour repeats. Copy that helper across 1,000 apps and you get 1,000 extra proxies, the sidecar tax. A sidecar is a proxy copied beside each app. It inspects and routes traffic without changing app code. Useful, but one app means one helper. At scale, the helper becomes a fleet. Follow one request. The app hands data to Linux. Linux redirects it up to the sidecar, which checks it, opens a second connection, and sends it down again. The destination repeats the detour in reverse. 12 visible steps. Exact counts vary. Remember the shape: down, across, repeat. And sidecar looks cheap. Scale creates 3 bills: memory for another process, latency for the detour, and operations because app and proxy must start, upgrade, and stop together. A tiny toll multiplied by every pod, and every request becomes architecture. eBPF moves simple decisions into Linux. A tiny program is checked for safety, attached to a useful moment such as opening a connection, and reads a shared map of destinations and policy. The point? Decide where traffic already is instead of sending it out to a helper and back. Those useful moments are hooks before the first packet while traffic moves or at the network card. Names can wait for part 2. Remember one rule: choose the earliest safe moment that already knows enough. Replay it. Checkout calls payments. With sidecars, the packet climbs into a proxy, drops back to Linux, crosses the network, then repeats that detour at payments. With eBPF, Linux checks policy, finds a healthy payments pod, and forwards directly. Same work, shared data path. 12 illustrated steps become 7. Checkout calls the stable name payments, but pod IPs change. Before any sidecar handles traffic, the node must pick a healthy backend. In a common legacy setup, kube proxy programs iptobles rules for services. As those rules grow, they cost more to update and traverse. eBPF uses a map for direct lookup. Separate win. Replacing a sidecar restarts every pod carrying it. Updating node-level eBPF leaves apps running. Honest caveat: eBPF excels at network basics, destinations, identity, policy, and encryption. HTTP adds meaning, paths, headers, retries, and login tokens where a proxy still wins. So proxies become shared and selective, not extinct. The trade: modern Linux, larger failure scope, and new debugging tools. The promise is fewer proxies used on purpose. Keep one sentence. Put network basics in Linux. Keep proxies for application meaning. That is how eBPF replaces sidecars without replacing every proxy. Connect hooks, traffic control, and XDP belong in part 2. For now, ask, does this job need HTTP, or does it belong in the kernel?